Hello and welcome to Lecture 4 in Thermochemistry, Communicating Enthalpy Changes. Here we see a listing of knowledge outcomes prescribed by Alberta Learning. Hopefully you're reviewing them from time to time to get a sense of your mastery of the material. There are a number of methods of communicating enthalpy change for a chemical reaction. Most of them are quite informal. We're responsible for learning 4 of them. These 4 include a thermochemical equation. Secondly, a thermochemical equation with enthalpy notation attached. Thirdly, simply enthalpy notation, also known as delta H notation. And fourthly, using a potential energy diagram. And we'll review these by way of example. The standard molar enthalpy for the formation of magnesium carbonate is negative 1095.8 kilojoules per mole, and they want us to report this using the 4 methods. Use of the word standard means that we're talking about SATP conditions, which allows us to tabulate many of these results. We use a not sign, which I'll show you in a minute, to indicate standard conditions. We're talking about the formation reaction. Hopefully we recall from grade 10 that formation of a compound typically implies from its elements in their standard condition. So our first step in reporting this using a thermochemical equation then is to come up with a chemical equation. We do so by starting with the skeletal reaction, and we see that here. We see our formation of 1 mole of magnesium carbonate from its elements in their standard state: solid magnesium, solid carbon, and O2 gas. We then balance the chemistry, and that requires us to use a fractional coefficient for the oxygen, and hopefully we're comfortable with that. We then add the enthalpy as a term of the equation, and you'll see here that the enthalpy is a negative value. This means this is an exothermic reaction. It's producing energy just the same way it produces any other product, and we show the enthalpy loss as a product in the thermochemical equation. So here's our complete thermochemical equation for the formation of 1 mole of magnesium carbonate. A variation on that then is our second method, which is, and again here we say that, we note that since it's an exothermic reaction, energy is being released, the enthalpy change is added as a product of the reaction. Our variation on that then is a thermochemical equation with enthalpy notation. So what we do is we pull out the enthalpy. On the left here you see the balanced chemistry, and on the right we see the formation enthalpy, delta FH naught, and the naught means under standard conditions, SATP conditions. There's a slight variation on this which would also be appropriate. We're producing 1 mole of magnesium carbonate. We see that in the chemistry. And therefore it's appropriate to report this as the standard formation enthalpy of 1 mole of magnesium carbonate. And that changes our units to kilojoules per mole, as we see here. Both of these methods are equally appropriate. Our third approach then is to use enthalpy notation alone. And it's important to show as much information here as you can to be able to generate a thermochemical equation from the enthalpy notation alone. So here we see the standard molar enthalpy of formation for magnesium carbonate. We have all that information wrapped up in this notation. And again, we have the same value as we've had previously. And because of that, you often see delta H notation with subscripts like form for formation, decomp for decomposition, nu for neutralization, and so on. Our fourth method then is drawing a potential energy diagram. And the potential energy diagram for this particular chemistry is a line diagram that plots potential energy against time. And here it is. So the y-axis is potential energy. The x-axis can either be time, or reaction progress, or reaction coordinate. These are all alternatives. And I'm just showing all 3, but you'd choose one. You'll see that the reactants are higher in potential energy, the product is lower in potential energy. So this is an exothermic system. And of course the difference in those potential energies is the enthalpy loss for the chemical system, shown here, and represented by the downward pointing arrow. Here we have 2 general potential energy diagrams. The one on the left shows a decrease in enthalpy, representing an exothermic chemical reaction. The one on the right shows an increase in enthalpy, representing an endothermic chemical reaction. course, the difference, the downward arrow on the left graph represents the loss in enthalpy of the chemical system, whereas the upward arrow on the right graph represents a gain in enthalpy of the chemical system. You'll notice that there's no scale on the y-axis in either of these, and this harkens back to something I've said before. It's really impossible to determine the total enthalpy of a chemical system. Similarly, it's impossible to determine the total potential energy of a chemical system, which is what the y-axis represents. So we very seldom see a scale on this y-axis. It would be unusual. So below we see the potential energy diagram for photosynthesis, and they want us to use the other three methods to report the same information. And here's the potential energy diagram. So potential energy on the y, time on the x, and you see our reactants are lower in potential energy, our products are higher in potential energy. And the difference, of course, is change in enthalpy. To report this using a thermochemical equation, we're talking about an endothermic reaction. So energy goes into the chemical system just as any other reactant, and you see that here. The enthalpy is reported as a reactant in the system. And I want to direct your attention to the water coming in liquid form. This L represents a knowledge outcome under Albert Olring's curriculum. They're invested in ensuring that you recognize that water goes into photosynthesis in liquid form and comes out of cellular respiration in liquid form. Whereas when we burn hydrocarbons, water comes out in water vapor. Now, they're trying to reflect the chemistry here, but for reasons known only to themselves, they want to ensure that you sort of give that back to them as an answer. So review that knowledge outcome and sort of fix that into your thought process, that we're dealing with liquid water when talking about biological processes like photosynthesis and cellular respiration. All right, so there's our thermochemical equation. The reaction is endothermic, so the enthalpy is shown as a reactant. Our two remaining methods then are a thermochemical equation with enthalpy notation. So here on the left, you'll see the chemistry. And on the right, we have enthalpy notation. Delta H for the photosynthetic process, 2802.7 kilojoules. And then using delta H notation alone, we have delta H for photosynthesis for producing 1 mole of glucose is 2802.7 kilojoules per mole. I have a few questions here before I conclude, and after that I'd refer you to any homework your teacher assigns. So here we have a question. The reaction represented by the potential energy diagram above is, well, is this an exothermic or an endothermic reaction? We're showing reactants that are higher in enthalpy and products that are lower in enthalpy. I would submit that this system is losing energy and therefore it's an exothermic reaction. Therefore, C and D are out. If energy were included as a term of a thermochemical equation, it would be A. Well, it's an exothermic reaction, so therefore energy is produced just like any other product, and the energy would show up in the equation as a product. And our answer here, therefore, is B. Here we see what appears to be a combustion reaction. We're burning ethanol. We're burning alcohol. And you'll see that it's a highly exothermic reaction, negative 1366.8 kilojoules. And the question here is, in the above reaction, the reactants have either more or less energy than the products. Well, it's exothermic. That energy must be stored in the reactants, but it's lost to the surroundings. So the products don't have that energy. So in the above reaction, the reactants have more energy than the products, and choices C and D are out. If energy were included as a term of the equation, it would be A. Well, again, we're talking about an exothermic reaction. Exothermic reactions produce energy. So again, it would be reflected as a product in the thermochemical equation. So therefore, the answer here would be B. I think I have one last question. Yes. The potential energy diagram for the above reaction would most closely be approximated by. So here we have our reaction, and we're showing enthalpy as a negative value, exothermic reaction. So we need a potential energy diagram for an exothermic system. I would submit C and D are both out. C and D both reflect endothermic reactions. A and B represent exothermic reactions, but you'll notice there's a problem with A. A is reflecting a positive enthalpy change. Positive enthalpy changes typically reflect endothermic reactions, not exothermic reactions. And therefore the correct answer here is B. So that concludes my lecture on communicating enthalpy changes. I'd refer you to your teacher's homework in this regard, should you have any more questions, and hopefully you found today's lecture helpful. I'll see you again next time when we talk about Hess's Law. Thank you.